Hello everybody. My name is Delsing. I'm a professor at the Lulea University of Technology in Sweden, and I'm grateful for being invited to this keynote. And the topic on my talk will be about production automation digitalization and software. Is it a problem or the solution? Looking at production and automation, or production automation and its digitization, we very clearly will have cyber physical systems around. We will very clearly have system of systems and the omnipresent IoT as well. And we will look forward to models like the RAMI model that I put on the slide here. But what is the market saying? The market was analyzed by Artemis, the Industry Association of Embedded Software, last year with the support of the Advanced company. And it's very clear that if we have a value chain from electronics, components, and systems, from the equipment tools, producing electronics, producing the embedded packages and the standalone embedded systems, this market has a very interesting growth. Yes, it's large. All these things are used in transportation, smart mobility, health, well-being, energy, etc. And later on, all these things will start to work together. This is what's the fifth area here in this value chain, which is depicted. And it's very clear that most of the market value will be, and the big growth will be in the downstream here, so in the system of system. Interesting numbers in this analysis where we see growth data for this fifth area system of system from about 500 billion euros per annum from 2018 till 2025, where the prognoses are 3.9 trillion to 11.1 trillion euros in global turnover. So we see a very strong market pool for going this direction. And of course here, the digitization automation in industry is one of the key players in achieving this. So current production, we see very much within single enterprises, but we also see that these enterprises are using a lot of subcontractors to really move their production. And this is a very clear change that we will see stakeholder collaboration to achieve the production. We would see a very much a stronger supply chain interaction, and we will also see a very much integrated life cycle domain for obvious reasons connected to circular economies, environmental impact, etc. And all these players will need to work not in a chain, but rather in a network where information need to flow between various players within the company, between companies, from individual components, like here a ball bearing, into a larger machine, an operator, and groups of operators or companies that is then involved at various stages. So this will become a more and more complex situation that we see benefits from. This is the market pool. And but we need to be able to build these type of systems, since we do see a lot of new requirements. very many people have identified information interoperability, security, safety interoperability. Who owns the data? Can we access the data? How do we handle real time? Since real time will be there, yes. How do we create trust of what has been done, trust around data? Can we create machine-to-machine businesses? Can we also create real-time monetization? Engineering will move into a real-time situation, etc., etc. These are, very many of these are very new requirements compared to the existing automation in current industry. So what do we need to integrate? We need to integrate sensors, actuators, etc., all the way down to organizations, managements of this, the engineering procedures, tools, engineering procedures. All these need to be looked at into a more homogeneous, in a more homogeneous fashion compared to how we operate today. So one example here is when we see that operational technology meets with ICT, and the operational technologies, they were started to be developed in the 80s. And the ICT, current ICT domain is very young. The difference in technology and attitudes and culture and policies is very large, from things that should work 24/7, 365 to things that should work for a short time, or we just try to get it to work. And we have very different type of businesses involved in this. And this is one example of the gaps that we need to cover. So if we look from the different paradigms that we see now, we see the cloud, we see what people talk about fog and edge, and edge, I here also call it both fog, edge, and local. When we move to high performance computing in the fog, and where we have tons of involved IoT devices, extremely distributed. This will lead to situations where we have very large scale IoT and system of system that's emerging, and also have very evolving characteristics. For example, we will see very large scale system of systems in the ballpark of 10 to the 5 to 10 to the 10 of these Internet of Thing devices. We will also see a lot of more runtime dynamics, functional evolution over time, that things will scale, they need to scale, they need to be able to handle real time, etc., etc., etc. Well, what are the things that we then really is building this on? If we take production assets, if you take a paper mill or a mine, these machines, these operations becomes very old. If you take energy production, they will not just last 3 years like a cell phone, but they will last from 10 to 100 years, which means we have a lot of old technology. The automation technology that we have put in now for the last 50 years into these large assets, they have probably a lifetime of 5 to 20 years. Electronics older than 20 years are very rare. It might be some examples, but in most cases, electronics lives in 5 to 20 years time range. And then we have people who is working together with this. They are used to smartphones, tablets, etc., which has a life cycle of 1 to 3 years. If you take both the automation technology and the personal technologies, there is software on them. And what is the life cycle of these? I would say from days to a couple of years, in the best case. Interesting example is, for example, the updates of Tesla software, which happens a few times a week. And what about business models? Do they live forever? No. Many business models, we will see updates of business models that are updated in very short time frames, months. And some business models will live for much, much longer time. But this will also become a much more dynamic situation. So what about the software and hardware diversity in all this, from the cloud to the edge? We are talking about high performance computing, both at data centers and at the fog at the edge, and also even down to the very local things with what we now call the embedded high performance computing. And there is all these things are then moving. If we go to the very tiniest thing, we talk about resource constrained things on the internet and emerging energy constrained things of the internet. And there might be enormous numbers of these down here. Data centers are not that many. We probably can count them in thousands around the globe, but we are not talking about billions, which is what we are talking about when we talk to the things of the internet. So we have a huge computing platform diversity in terms of what type of microcontrollers and also emerging technologies there where we not even have possibilities to write code for yet. We also have software diversity. So how many operating systems do we work with? How many protocols do we work with? Which are the various security paradigms we work with? And even worse, it comes to when we talk about the data that we are trying to generate and transfer. They will be extremely diverse. So can never get to integrated automation, digitalization of industry or society if we bring it even further. We need to understand that the requirements are moving targets. We have multi-billion lines of code already. A lot of this is proprietary software. A growing part is open source software. We have various software licenses. We have version incompatibilities. We have bugs. We have, I would say, lousy documented code, etc. So can we bring all these soup together? This is one of the big challenges that lays ahead of us for this era. So what may bring us to this larger scale of automation and digitization? For obvious reasons, we'll need architectures. We need interoperability. We need something that we start to call composability, that things should be able to work together without screwing up the rest of the system. We do need integration platforms. We do need updated engineering procedures. Engineering will not only be design time, but it will very much be runtime in the near future. We need new engineering tools, tool chains, and that we also need model-supported engineering, machine-supported engineering, autonomous engineering, solution self-adaptation, business automation, etc. So let's have a look into some of these. So let's have a look at the emerging integration platforms, which do have architectures they need, interoperability, composability, so on. What we find here is that almost everything that we see is based on the service-oriented paradigm, which was invented by IBM in the 70s when they started to look at how to integrate their 7 lines of incompatible computing platforms that they had developed over the years. And we do find a number of these platforms, like the Eclipse Arrowhead, Fiverr, Eclipse Basics. Interesting, all of these are open source. There has been made some comparison between these type of IoT system architecture and platforms. And there is an interesting paper by Christina Paniaga that compares these with a number of automation industry related features. So have a look here and try to make your own a view of what you would like to see. So what about interoperability and composability? Can machines detect mismatches that creates non-interoperability and composability regarding what protocol machines talking, which is the security paradigm, what are data models are used, which are the functional models, which are the policy models, and we will need to have even further more advanced information about what machines are capable of doing. But can machines detect that today? We do see possibilities for this, but on a general, the answer is no. But this is still an approach that is of clear interest. And if we can do this detection, can we then instantiate translators that enables interoperability and composability? So, like the figure here, we have a system A with a service contract of a service A with a service contract of a certain type, and then we have someone that should consume that service with a service contract A star, and they are of course not equal, but can we provide translators that at least makes it possible to transfer data, but also some of the non-functional properties from a system P to a system C. This is the interesting approach. We do see results in this direction. There is interesting publications by Hassan Derhami, for example, where he created interoperability between various SOA protocols like HTTP, CoAP, MQTT, and also encodings, for example. And working code for these kind of things can be found, and here is an example of this from the Arrowhead framework. Can we translate the data, the semantics of data? There are people looking into doing called ontology-based approaches. Some interesting work being done in the University of Lisbon, and where they annotate semantics to create some super ontologies that can be used for moving from one semantic from one ontology to another with a large portion of machine support. There are other approaches where machine learning is used for creating translators. This is some interesting work by Jakob Nilsson and Fredrik Sandin, and they are currently playing with possibilities of using both the data but also metadata about the information to achieve some reasonable translation. We see current results in where we can get accuracies of 50, 60, 70, 80% of course, this is reducing the need for engineers to do the complete translation. So it's a step forward, but this is, I would say, one of the more promising results to create autonomous and automated machine translation of data semantics. If we look at the engineering side, then, so I said previously, engineering procedures will move from design time to runtime. We need integrated tool chains. We need model-supported engineering, and where machines can do a lot of more engineering than we see today, and that this engineering also can be autonomous, where the need for engineering can be detected and communicated to machines. And this will, in the end, also create solution adaptation capabilities, where self-engineering, self-validation, self-verification, self-deployment are concepts that is necessary. It's interesting to see that we see that engineering processes and tools also starts to be integrated using the service-oriented architecture. This is a very recent paper by Gianvito Orgese et al., where they clearly shows how an engineering process for creating automation can be modeled using service-oriented architecture. Can we look at the business relations between stakeholders, for example? Here is just a simple diagram where there is a component supplier that gets an order from an assembly plant for something. This one needs a transporter to transport the stuff to the assembly plant, and this is the complete business process in a simple model. Can we automate this business model? Today, this is mostly handled by paper, and there are clear approaches here where we can automate this and where we can secure the various type of data transferred. So we can create a proposal, we can sign this and put it into a trusted log, and basically a distributed ledger between the two players involved, and the one here can accept this business proposal and send it back, and we can then say that yes, we can create this into an exchange at both places where we have an acceptance, and this can then be complemented with key performance actions, modeling, or indicating that we can get different payments dependent on different quality parameters, etc., etc. But it's clear that all this can be automated. We don't need to have a procurement office to do this. Machines can do these things on their own. And we do see emerging business situations where this is there. And we also see that this will not only involve ensuring that we have the data for it, but it will also involve the complete transaction. Both the movement of goods and the execution of what should be done with that goods, but also the other part of it. So the money transaction, the transfer of money, is the other part of that transaction. So this can also be included here. Let's look at the engineering process. Can we use models to support engineering? And the graph here is a SysML model of a small control loop. Yes, we can make these models. We can from these models have machines to create a lot of the code that's necessary for it. And if we then have situations where we are adding things to our client, we can identify what is this, or we can just get the model of that, and then the rest can be engineered in an autonomous fashion by the involved machines. And this is, of course, a step into this solution adaptation by self-engineering, self-validation, self-verification, etc. In this case, we are using SysML and also the emerging SysML2 standard for creating this. So if we move back to this RAMI stuff, so the production automation, which is basically this axis of the RAMI model, yes, we can create automation, we can create control and all these kind of things with this service-oriented architecture things. Can we look into the production life cycle with the engineering, the maintenance? Yes. This has been clearly demonstrated in various projects at European scale. And can we move from assets to business, so automate machine-to-machine business transactions? And I gave some indications that, yes, we do see emerging technology for this. And the interesting thing is that all this can be integrated with SOA-based platforms. So a lot of the literature indicates that service-oriented really can support us in moving this way. So which are the identified approaches that I've here kind of elaborated a little bit on? So architectures and integration platforms, yes, they are based on service-oriented architecture. There's interoperability and composability. Translation seems to be the way of creating autonomous automated engineering. All other approaches that we have seen will require human engineers to do the job. What about the engineering processes then? And it's very clear that we can create or automate a lot of the software engineering, provided that we have the right tools and the right models for it. Can we integrate the business models and business execution? Yes. It seems very likely that automated machine-to-machine business processes can be reality in an automation industry, automation digitalization environments, quite short time frame. All of this also can be supported by model-supported engineering and modeling languages like SysML and the emerging SysML2. This is necessary to really achieve what we are looking forward to. So what's the message in the end? System of systems and systems of cyber-physical systems already are and will be the critical parts of future automation digitization in not only industry, but in society overall. And it's also very clear that software is the key enabler to get these system of systems and system of cyber-physical systems to really work. But it's also clear that we need to agree on a few key concepts to really start to reduce the complexity of the world we have today. We cannot expect standards to do this. We already have too many standards, but some fundamental concepts like the ones I had in my previous slides. And we also need automated approaches to bridge mismatches between various systems. But it will require a capability to actually detect and automatically detect these mismatches and the nature of the mismatches such that they can be bridged using some type of translation approaches. And to enable all these things, we need to have models of the system of systems, of the system of cyber-physical system, and the software that is involved to create these functionalities. These models will be necessary to allow us to move forward into the future, what everyone is talking about, but we see tons of interesting, how to say it, tons of challenges that need to be bridged, such that we can make this with an economy that will be that will scale. So that's all from my side. I hope you have some interesting questions that I will try to respond to. So thank you for listening.